The next speaker is Gianluca. I know him very well. Gianluca Parma. His presentation is about multi-plate clutch lubrication and cooling. He holds a master's degree in aeronautical engineering. And after that, Gianluca spent 2 years on research as a research assistant at Politecnico di Milano studying numerical methods for ice accretion prediction for aircrafts and helicopters. Gianluca joined the Particleworks team at Enginsoft in 2018, and he has worked on several industrial projects related to powertrain, lubrication, and cooling. Gianluca, please.
Thank you, Massimo, for the warm introduction. Can we have the slide, please? Thank you. So the title of the presentation is Multi-Plate Clutch for Agricultural Application, a novel method for oil flow and heat transfer analysis. So this activity was done with a French transmission manufacturer, which is part of the class group. And in particular, we will see a way to evaluate HTC, HTC transfer coefficient distribution, and everything related to thermal and cooling of a multi-plate clutch. Okay, so let's start with a brief introduction. So when you have to transmit high torques, especially for example in agricultural application, you need multi-plate clutches to distribute the friction on different plates. And during the engagement phase, the friction increases the temperature of the materials, which in this case was the temperature can increase up to more than 200 Celsius. And if the cooling is not properly set up, you can have a reduction of efficiency of torque transmission and also increasing in failure risk. So here you can see a section of the clutch that we will study. It's a 8-plate clutch. And on the right side, you can see a detail of the disc. So you can see the grooves on the disc. And when the plates of the clutch are all engaged, the oil, which we will see the path of the oil, but the oil that flow on the disc will be only able to pass through these small channels, okay, these small grooves. So again, oil flow and oil distribution has a key role in thermal management in general. And so in this study, we wanted to evaluate wet areas and extract heat transfer coefficient distribution in order to understand if this configuration, which is a real product, which is now on real agricultural machines, tractors, if this current situation is good and where can be improved. So two different working condition have been analyzed. So in particular on the left, we see the cool down condition in which the discs are not engaged. And on the left side here, we have the engine. So there is an input shaft which is rotating, but no torque and no motion transmission. And this is, in this case, discs are not engaged. On the right side, the other case, it's the engaged condition in which discs are in contact and torque and rotation and motion, it's transferred. So in the end, after the wet areas analysis and heat transfer coefficient distribution, we ran an additional steady state thermal analysis to see temperature distribution inside solids. Okay, I think we all know Particleworks method, so I can maybe skip this note about the method, but just a remark about the heat transfer coefficient calculation. So in Particleworks, you know that you can have different models for HTC. In particular, the standard one, the default one, is the flat plate correlation, but you can change it arbitrarily. And for this study, flat plate correlation was good because we are mainly interested in flow between the disks. So we have two plates, parallel plates, and the flow between the two disks. So flat plate correlation was used in this study. So as you know, HTC does not require temperature field. And this means that simulation is faster than a thermal analysis. Okay, so then after the HTC calculation, we will extract the maps of the HTC, so the HTC distribution on the walls, and then we will use this information for the second step, which is the thermal analysis and the the calculation of temperature distribution within solids. This step will be, it's done here in Particleworks, but if you want, can be also done in a different tool. So let's have a look to the geometry to understand how the system works. So here you can see a section of the clutch system, and on the left a rendering, okay, just to understand also from the outside. So the system is composed by an input shaft linked to the engine, okay, which is rotating, and all the gray parts are linked together, okay, so they share the same motion. We have a pressure plate, which is the element that can compress the disk and then keep the contact between, let's say, gray and blue disk, and in this way you can transmit the motion and the torque to the output shaft. So output shaft and blue disk are the blue elements, and here on the bottom you can see an annular, this is an annular chamber, which will be filled with oil. So we will see the path of the oil, but an annular chamber here, and you can see some holes here to make a connection between this internal chamber and the disk. So the idea is that the oil path is this one highlighted by the arrows. So oil comes from the input shaft, from the inside of the input shaft, pass through these some holes, radial holes in the input shaft, fill this annular chamber. Then there are some gaps. Then the oil can flow out. It's centrifugated, goes in this internal chamber, and then pass through these holes, reaches the disks, and passing through the disk can cool the disk, and then it's collected and removed by this opening in the external cover. So this is the flow, and the idea is to study what happens to the oil, how it distributes. So let's have a look to the configuration more in detail, the working condition that we studied. So the first one, we can call it cool down condition. It's the most critical condition because here you don't have contact between disks, and typically it's the phase after the engagement or just before the engagement. But if you are after the engagement, it means that those parts, it's quite hot, okay, and you have to cool down in an efficient way. But the idea, not the idea, but the problem is that in this phase, you don't share the motion. So left part, it's rotating, input shaft, it's rotating, but blue part, it's fixed, okay, because you disengage the disk. So on the blue, the oil in contact with the blue part will not get any centrifugal force, which helps to pass through these radial channels here. Okay, so it's critical because you don't have the additional effect of centrifugal forces. But on the other side, from the simulation perspective, we have bigger gaps, 0.4 millimeters, which is the distance between the disks. The second configuration, it's the engaged condition in which all the disks are in contact. And from the point of view of the simulation, it's more demanding because the gaps are smaller, only the groove size, which is 0.25 millimeters. So oil can flow only through the grooves. But we have centrifugal forces because also the output shaft is rotating. And so the oil from the internal chamber can, let's say, more easily flow and reach the disk. So just some consideration about particle size. So you know that when you define particles, when you decide particle size, you have to deal with the smallest gap that you want to study. And in this case, the smallest gap that we have are located here. So the connection between the annular chamber, so input shaft, oil goes through the annular chamber and goes out from this small gap, and then it goes out radially, okay? This gap is 0.5 millimeters. The other limitation, we said, it's the 0.25 millimeters space in the grooves when the disks are in contact. So our limitation for particle size, it becomes 0.25 millimeters, quite small. And so we decided to use, we had to use a particle size of 0.1 in order to have at least 2.5 particle size in the smallest gap. And using this particle size, the simulation have 90 million and 120 million in the two configurations, so a quite high number. But we reach a steady state in just 2.53 seconds. So the simulation time is not so long, and the simulation it's feasible. So also with this high number of particles, it's feasible. Here, just a summary of the simulation setup. And let's see some results. So let's start from the cool down configuration. We will see fluid distribution and the transfer maps, the transfer coefficient distribution. So here we can see the oil distribution in this video. So internal, here there is an inflow which generates oil. We don't need to simulate the entire channel. And then the oil spread in the internal chamber. So here we have disconnected motion. So right part, it's not rotating, no centrifugal forces. And this is a section to show the internal radial channel, which brings oil from the internal chamber to the friction disk. And from here, you can see that, for example, in these two parts here, two regions, the oil flow, it's not constant like in the other regions. So it seems that it's not uniform in all holes. And this is interesting because if you want to cool in the same way all the disk, you want a balanced flow across all the disks, all the holes, okay? Another thing that we can observe is this accumulation on the bottom, which is not present, is not there, or at least it's less on the top. And it is due to the gravity, because gravity in this case, it's a roll, okay? Because on the right side, nothing is moving, and here we have no centrifugal forces. And then another thing that I wanted to check was what happens in this part. So here there is a ceiling, and when we don't have motion, we can see that there is some leakage in this ceiling. So something that in new configuration could be probably improved. Okay, so we saw that it seems we don't have a balanced flow across the channel, the radial channel. So we created a probes and measured the flow rate as you do. So here on the left we have the top channels. so here. And on the right side, we have bottom channels. And the gravity vector is in vertical toward down here. Okay. So this is the detail and just an animation. And if we move to the measurements, we can clearly see that both in top channels and bottom channels, we have not a uniform distribution. So this is a percentage distribution respect to the total, let's say. So 12% should be all the same, should be the value if all the channel has the same flow rate. But you can see, for example, here we have some holes. So we can say that we have no balanced flow in axial direction. But then if we also measure the total amount, so if we sum all these 8 on the top and all these on the bottom, we can see also that the bottom channel in total brings out more oil, okay, due to the gravity, because gravity vector it's downward. So we can say that we have no uniform flow rate, and we can expect no uniform cooling in general. We will see how, but this is what we can expect. This is a section. This video, we can see the oil distribution. This is a section between disk, let's say number 5. We can say more or less in the middle of the clutch. You can see the oil is centrifugated here. You don't see the grooves because the 2 disks are not in contact, so you don't clearly see the grooves. And this oil, it's yes, centrifugated. From that oil distribution, using a mapping, was possible to get the average wetted regions. And from the average wetting region, so wetted regions and HTC are strictly related. So in this slide, we can see the HTC along, let's say, the shaft. So the first map refers to oil close to the pusher disc, to the pusher plate. And you see there is a higher value because there is some accumulation of oil. There is some sort of reservoir that can be seen in the section. And then if you move to the other side of the shaft, you see that the HTC seems similar. Okay. Okay, so let's move to the engaged configuration. Okay. So here again a section of the system. Here you don't see the channel just because it's not a fixed section. So the section it's not rotating together with the shaft, but it's just fixed. And you can see the oil distribution. So also here, just this is a detail on the channels. Okay. And also here you can see that in this area, which is the same area as before, we have a non-constant flow. And probably here, this region, it's a region where the flow has some disturb, okay, because the flow comes from here, we say, but then the oil flow impact on the spring. This is a spring which is here to balance the pressure of the pressure disc, okay? So the oil goes out from here, impact on the spring, and then disturb this. You see here there is more turbulence, let's say, respect to other region like here. So probably there is an impact of the position of this element which can interact with these radial channels. And this is something interesting. Okay, here you see the reservoir that I mentioned before. It's also there in the rotating, in this configuration. And so this is a sort of reservoir which brings oil in the first disk, more oil to the first disk. Okay, that's why the first disk had high HTC values. Okay. The same way, this is the section between disk number 5 again, same position as before, and here you can clearly see the shapes of the grooves. Okay, because now oil can only pass through a disk via the grooves. Okay, so you can clearly see the groove shape. And if we do a mapping to detect the wetted areas, okay, you can see that there is a sort of pattern. So blue, this is the average, instantaneous value of the number density. So you know that blue values, low values means low wetting, and red means high wetting. So we can clearly see that there is a sort of pattern in which we alternate wetted region to less wetted region, and so on. Okay, and this was interesting. So if we analyze the path of the oil flow, so the orange arrow are the radial channels which brings oil to the disk, and we, at least the manufacturer, expected that oil passes through these radial channels, at least. But due to the rotation of the disk, the motion composition of radial velocity and rotation brings oil not in radial direction, but in this inclined direction, okay? And in this way, we can see that for this reason, we can see that there is some areas more wetted, just always behind the position of the radial channel. So again, from wetted maps on the left, we extracted the average HTC distribution, okay? And you see that in average, it's a little bit different. I mean, there is more coverage because now here, this is the average, also the wetting, but there are still parts of the disk that are not well wetted and with a low value of HTC. So again, low value of HTC means low cooling. So again, we can expect a non-uniform cooling on the disk. Okay, and for this, only for this configuration, we ran a conjugated transfer analysis to calculate temperature inside the walls, inside the system. And as you probably know, the steady state approach requires two subsequent, let's say, simulations. So the first simulation, it's only oil, in which you extract the heat transfer coefficient distribution, okay? The part that we already did and we already saw in the presentation. So you extract the oil flow and you map the heat transfer coefficient. Then you create, the maps, of course, of the heat transfer coefficient. And then you build a new model in which you import the maps of heat transfer coefficient and the temperature, because you also need temperature, as boundary conditions. Then you have boundary condition, you can apply source of powers, for example, and then you can run the steady state thermal analysis to get temperature distribution in solids. So in this slide, let's have a look to the boundary conditions that we had. So we apply the source of power on the disk, okay, in these red regions. So the idea is that the disk have been just in contact, so the peak of power that we have. Then we applied on all surface wetted by oil, we apply the maps calculated by the previous simulation, so everywhere inside, between the disk, but also inside the chamber, the big chamber. And then on the outside, we applied HTC and temperature towards the ambient, okay? So here some results, some temperature distribution inside and outside. So this is the outside temperature distribution. On the right, the inside distribution. And a couple of sections, lateral section and front section of a disk, again disk number 5. And you can clearly see that there is no balance from top and bottom, for example, but also on the disk. So probably this is related to what we saw before, so non-uniform oil distribution, and yeah, for example, the effect of the spring inside, which create a non-uniform oil distribution on disk. Okay, so in conclusions, so we ran a simulation of a multi-plate clutch to evaluate oil distribution, wetted areas, and the heat transfer coefficient in 2 different configurations. So the main challenges were rotating parts and particle size, which is quite small compared to the size of the system. And simulation had 120 million particles, the most demanding one. And at that time, so a few months ago, there was no possibility to run with the nice new feature of multi-resolution. So this is something that can be included in the workflow to reduce simulation time. So for the next simulations. And the main results are that in both configurations, we saw that the oil distribution was not uniform. So some disk gets less oil, which means less cooling effect. So the position of radial channels can be optimized, also including the interference with internal elements like the spring. And for the engaged condition, again, the oil distribution on the disk, it's not uniform due to the rotation of the disk and the motion composition, let's say, with the oil. So the grooves pattern can be improved in order to have a more uniform oil flow. And just to conclude, a rendering, and to thank you for your attention, a rendering done, so simulation done with Particleworks, then from Particleworks, simulation solution was converted with Simunima, a new tool which will be presented by Prometech soon in my presentation, and then a rendering done with Blender. So thank you for your attention, and if you have any question, I'm here.
Very interesting presentation. Question about the inflow. Where did you put the inflow of the oil? I don't know if I didn't catch it.
No, probably I skipped that. The inflow was placed here, just before, let's say, the radial, these internal channels, because we didn't. So there was no need to simulate this part, which with the particle size so small are wasted particles. So probably it will affect the cooling of this part on the global temperature distribution, but at the moment the focus was more on this part. So it was.
Thank you.
Thank you.
How long it took for the full simulation with 120 million particles?
Okay, so this simulation ran about 1 week on multi-GPU. It was 4 GPU because also the memory required was, but Yes. I think that with the multi-resolution feature, this time will drop, or at least will decrease significantly, because on this region, center region, we don't need small particles, so we can refine only what happens inside the disk and in this gap here.
Thanks.
Hello. Hi. You mentioned steady state simulation. So I assume you use a constant power input. There is a way to add power as a function of time, so you can run a kind of engagement?
Okay. Yeah, it's possible. You can create a table, Excel file with time and power, or volumetric power, and then you can input. So you can do it.
Okay.
Thank you for presentation. I have some technical question. If you run the simulation by the multi-GPU, you will always connect the GPU cards by the NVLink?
Okay, so you can do it, but it's not mandatory. So if the GPU cards are on the same computational node, you can also use a standard, let's say, connection. Of course, if you have NVLink, probably the connection is faster. Maybe we can ask to the developer, but probably it's faster. But also without any NVLink, the scalability is pretty good. So it's when you double GPU, so you save more or less 40%, 45% of the simulation time without NVLink. I never tested it, but I think at least for me, it's good. Thanks.
Thank you, Gianluca.
Thank you.